Quantum mechanics, note number 4, the electron double slit experiment. From previous lessons, we found that light is able to act both as a wave and a particle. In physics, there seems to be a grand duality to nature. There's matter and antimatter. So would it be possible that if light can be both a wave and a particle, could matter itself also be a wave and a particle? Scientists in the early 1900s actually asked this question themselves, and they did an experiment to see whether or not this was true. First off, before we consider anything, let's take a look at the double slit experiment and see how particles would act if we send them through and how waves would act if we send them through. So for particles in the double slit, just pretend you have a styrofoam cup. You cut 2 slits in the bottom, you fill it with sand. What should we expect to see on the tabletop below or the screen? The sand should drop through both of the holes and end up in 2 piles. This is the classic behavior of a particle if it were to go through the double slits. The particles would pile up and we would see just 2 humps on the screen. They're only in one place at one time, so a single particle can only go through one slit or the other and land on the pile. And when it lands on the pile, it's able to collide. So we say that these particles are localized, and from those collisions, they spread out. Waves is basically a review of Young's double slit experiment. So let's say we have our slits and waves approach them. We know that as the waves get to the slits, diffraction occurs. The waves are going to bend as they go through those openings. But as waves go through one of the slits, they're going to interact with waves that are going through the other slit. And remember, we have constructive and destructive interference. This is going to produce an interference pattern on the screen ahead. We're going to have bright spots and dark spots if it was light. If it was water, it would be really high amplitude areas, and then we'd also have nodes. So if we give some vocabulary here to the wave interaction, definitely this is an interference pattern. Only waves can produce this. We say that waves are non-localized. A wave from one slit has to interact with a wave from the other slit to produce this pattern. That's the only way it will work. So what scientists did was, knowing both of these situations, they said, let's take a really, really small particle like an electron and let's send that through the double slit. So they boiled electrons off of something metal and put that shower of electrons through the double slit. Before we do this though, I want you to predict what type of result should we get with the electrons. So here we have our double slit. Electrons are lining up, we're ready to go through. When scientists did this, they put a whole shower through, so that means thousands and thousands of electrons all at the same time. Many of them bounced back, but a lot of them went through the slits. Here, the result they got were electrons were landing in piles, just like an interference pattern. This was totally odd. If we think of electrons as really small particles, we should have saw 2 piles of them as they go through. But for some reason, electrons through one slit were interfering with electrons in the other slit and giving us this interference pattern. They were acting as if they were non-localized. But how can they interfere to make this? This confused scientists. Could it be maybe the charge? Maybe the electrons were going through and repelling off each other. Maybe it's the size. Maybe we needed something bigger, or maybe something smaller. So to test this, scientists only sent through 1 electron at a time. If we send through 1 at a time, this will negate any problems we had with the charge. So here we're going to set up our double slit and line up our screen again. Only through 1 electron at a time. Again, we notice an interference pattern. If we just let the electrons land in piles, over time we're just going to see several piles along that screen as long as we don't look what's happening. But how is this possible? We know an interference pattern needs something from one slit to interfere with something in the other slit. How can that electron be interfering with itself? So there's two conclusions we can make from this. We know, number one, that electrons are acting as waves. We know this because it produces an interference pattern. And number two, there's places on that screen where the electrons hit and places where they don't. So this gives us a little bit of a probabilistic nature of the electron, where there's chances it's going to land in some places and then 0% chances it's going to land in others. This still confuses scientists today. We don't 100% know exactly what's going on. So back then, we tried to solve this problem. We wanted to ask what is happening. If we're sending through single electrons one at a time, which one are they going through? So scientists decided to try and look. They put a camera beside one of the holes. If an electron went through and it was notified by or seen by the camera, we know it went through that slit. But if it wasn't, we know it should have went through the other slit. When we try and peek, all of a sudden the electron goes back to acting as a particle, and we get two piles of them on our screen. Here, again, yeah, they behave as particles. For some reason, the act of observation disturbs the electron's behavior. Remember, when we observe anything, we have to bounce a photon off of it in order to see it. Here, the camera bouncing photons off the electron disturbs the electron and causes it to act as a particle. This is called the observer effect. So there's four main interpretations. The first one is the collapse interpretation. This is saying that the electron turns into a wave, goes through both slits, interferes with itself, and when it hits the screen, it collapses and turns back into a particle. Number two is the many worlds, saying that if there's two chances of things happening, the electron actually goes through both slits, but we see one and a parallel universe sees the other slit. Pilot wave says space itself guides the electrons. And number four, the Copenhagen interpretation says don't worry about it, just focus on the results. So if matter ultimately can act as a wave, what would be the wavelength of these waves? What would be the wavelength producing that interference pattern on the screen? This is something called the de Broglie wavelength, and it can be calculated using our momentum of a photon equation. Knowing that momentum is mv, we can rearrange for wavelength, and we get the wavelength of this particle is going to be h over its mass times its velocity. So we need a velocity of a particle in order to have a wavelength. If we don't have a velocity, the wavelength is undefined. That means we'd be dividing by 0. So let's try this in an example. Let's say a 5-gram ping pong ball is moving at 12.7 meters per second. Let's use this to calculate the de Broglie wavelength. So we're going to insert these values in a new equation, and we're actually going to calculate a wavelength that's really, really small. We're going to get 1.04 times 10 to the negative 32 meters. Now, this is very odd, and I encourage you to research some of this on your own. The four interpretations are very, very neat. Scientists either believe one or the other, but not many of them. This is the weird world of quantum mechanics.